All right, so who's excited about Big O? Somebody is. Okay, at least one person is. I thought you were like, let's fill that big hole. Not sure what hole we're filling. Good morning. Welcome back. So, today, we have finished our discussion of imperative programming that occupied us for the first month of class. We finished our discussion of objects, which has occupied us for the second portion of the class. And now, finally, we get to the good stuff. So from here on out, from now until May, we get to talk about some really cool things. Specifically, we get to talk about algorithms and data structures. So these are, fundamentally, programming is the core skill involved in computer science, and data structure and algorithms are the core concepts. This is the heart, the beating heart of computer science that we're starting on today. Thinking about how to solve problems, talking about classic algorithms, which we will discuss throughout the rest of the semester, for doing things like sorting, for doing things like searching. Talking about the classic data structures that enable these types of algorithms and allow us to store information and retrieve it and process it efficiently. Things like lists and trees and hashes, maps. These are things that, and graphs, which you guys will get some chance to work with on our next MP. So this is really great stuff. Now, along the way, we're still going to take our chances, and we're still gonna need to build on those ideas that you guys have seen already with imperative programming and with object-oriented programming. And we have a couple new things to talk about along the way. So there's a couple of new ideas, particularly in object-oriented programming in Java, that we still need to bring into the picture so that we can, finish the job and get to all this other good stuff. But this is really, the part of the class that I enjoy the most. I hope it's the part of the class that you will enjoy the most. It's more conceptual. It's a little bit less constructive. We're still gonna be building a lot of things. You guys are gonna still get a lot of chance to program, but we get to think a little bit more. And talk also about a lot of really interesting trade-offs, because that's one of the things that really, inhabits this space when we talk about algorithms and data structures, so trade-offs between different ways of doing things. Why choose one algorithm over another algorithm? This is the type of thing, as a computer scientist, as a programmer in the future, you'll have to make these trade-offs on a regular basis, and when people are evaluating your abilities to work in this field, one of the things that they're really gonna focus in on and hone in on is your ability to make these types of choices, to make these types of trade-offs. Everybody can figure out how to program this stuff. That's not that hard, right? Doing it well is still quite a beautiful skill, but being able to build the right things, being able to choose the right approach to a particular problem is really important. If you choose the wrong approach, it doesn't matter how beautiful your implementation is, it's still not gonna work well. If you choose the right approach, even if it takes you a little lot longer to get it to work, you've gone down the right path, so that's really important. Okay, so, we talked a little bit about this at the beginning of the semester, but we're gonna come back to it because this is now, core material. It's a core concern for us going forward. So an algorithm in computer science is a set of steps or procedures that we use to solve a problem. It's a problem-solving approach. An algorithm differs from an implementation of an algorithm, in the sense that an algorithm is an idea about how to solve the problem. Usually we can describe an algorithm in English. Sometimes we'll describe algorithms using pseudocode. That's not quite code, but there's a difference between the implementation of an algorithm, which you find described in computer code, and the algorithm itself, which we can talk about in English or in other languages, right? An algorithm spans multiple programming languages. Typically, given a good algorithm, I can implement it in a variety of different programming languages. So the implementation, the code is not the algorithm. The code might implement an algorithm, the code is not the algorithm. Algorithm is a set of steps. So as computer scientists, you guys implement algorithms by doing the things with computers that you know how to do at this point. So using them to perform simple calculations, storing the results, making simple decisions, and repeating these steps over and over as fast as we can. And what we're gonna see is that the object-oriented program, so you might wonder, like, why did we just spend this whole long, brain, mushing section on objects? I don't see that up there, but we're gonna use objects to structure our implementations of these algorithms and data structures. So that's where they come into play. It's quite powerful. A data structure, so these two things really go hand in hand. I know here we have a course called data structures, which is weird because it should be called algorithms of data structures. A data structure really never exists in a vacuum. It's always there because it allows us to implement certain algorithms on top of it. That's what a tree is for. We're gonna spend a lot of time talking about trees. We don't talk about trees just because they're pretty and fun to talk about. We talk about them because by structuring data that way, it allows us to implement certain algorithms efficiently. That's the same way with maps and lists and the other types of data structures we're gonna talk about. So data structures take these individual data values and they bring them into some relationship with each other. So when we talked about arrays, we talked about how arrays put items in order, back to back, one after another. We talked about trees and graphs and maps. We'll talk about different ways of structuring that, same type of information. But again, this is all done in service of some problem that we're trying to solve and some algorithm that we can now implement on top of that data structure. And what we're gonna do to implement those data structures, so here you see a little bit more about objects. We're gonna use primitive types and we're gonna create new Java classes to store and organize those data values. We'll use existing data structures like array, and then references play a really big role here. So you can think of a reference now as a way to establish a relationship between two different objects that are part of the same data structure. So a tree consists of a bunch of different objects that have references to each other. A list contains a bunch of different objects that have references to each other. A map contains an array that, contains references to other objects that might be stored in some other way. So references are really the thing that now allows us to bind different objects together. So if I take two Java objects and I want to establish some type of relationship between them, I can do that by using references. So creating a reference on one of them and setting it up so that it refers to the other. So now you're seeing more of where the objects and the references that we've been talking about over the past few weeks start to come into play in a big way when we talk about data structures. So again, these are two highly complementary topics. Whenever we talk about an algorithm, you might think, what type of data structure might I need to use to run this algorithm on top of? And particularly when we talk about data structures, you always want to think about, what is this data structure for? Why am I storing data this way? What can I do? What operation does it allow me to perform more quickly? What different algorithms can be implemented on top of this in an intuitive or an efficient way? Again, we don't, if we didn't need these extra fancy data structures, we wouldn't use them. If we could very simply implement everything on top of arrays, that's what we would do, but we can't. Turns out that these other data structures come in handy, allowing us to implement algorithms faster or better by using the extra structure that they bring to the underlying data. All right. And along the way, again, we're getting lots of practice using our imperative and object-oriented ideas. And we'll introduce a few more things as we go. All right, so again, we're sort of, traveling back in time to before we were talking about objects, and let's go through, just to sort of refresh your memory, an example of a little bit of an algorithm design question. And this is also going to illustrate some of the trade-offs in this space. Because one of the things about computers that's really magical is just how fast and powerful they've gotten, right? And this is something that, as a programmer and as a computer scientist, you want to be aware of. Both because, in certain cases, you can get away with doing things in a more simple way, but in other cases, something that seems to work in a limited way, when you run it on, fairly small problems, can start to perform extremely poorly once you run it on bigger problems that cause lots of issues, right? So we're gonna think, when we talk about algorithms and data structures, one of the things we're gonna talk about when we evaluate them and think about the trade-offs is things like, how long is it going to take? Okay, so let's think about GCD. So this is a math problem, and the goal here is to find the greatest common divisor of two numbers, which is the largest positive integer that divides each of them. Okay? This problem may seem abstract, but this problem turns out to have extremely important implications in the field of number theory and also to a lot of different applications in cryptography. So this particular problem. Okay, so I've got two numbers. I want to figure out what is the largest number that divides both of them equally. If those two numbers are both prime, what is the largest number that divides both of them equally? Sort of a special case, 1, right? Sometimes we call that relatively prime. Just because 1 is the largest number that divides, that is the GCD of two numbers, doesn't mean that both of those numbers are prime, but we refer to them as relatively prime, right? The largest divisor of both is 1. Okay, so, now there are complicated algorithms for solving GCD, and part of the reason is that this is a really foundational building block of other algorithms. If you can make GCD go faster, then you can make a lot of other algorithms speed up. And so if you go to the Wikipedia page, you can find, approaches to this problem that go back thousands of years, right? This is something that was studied by the Greeks, and, there's lots of very interesting approaches that you can use to this. However, we can also just try something a little bit easier and simpler as a starting point, which is never a bad idea when we're thinking about algorithms. So rather than, which I encourage you to do, go check out the Wikipedia page, look at all the really sophisticated, clever algorithms that have been used to solve this problem. But what's an easy thing to try? I give you two numbers, m and n, and I want you to find the largest number that divides both of them evenly. This is similar to a problem that we did earlier in the semester, but not quite the same. But what's a simple, straightforward, non-complex, easy to explain algorithm for solving this? Yeah. What's that? Yeah, so whenever we talk about algorithms, I want to encourage you guys to do one thing. Don't talk about programming constructs. Talk about the approach first. Then we'll figure out how to implement it. So the suggestion was, let's try a lot of numbers. Okay, I like that. Well, how are we going to structure our experiments so that we have some sense of, there's an easy way to keep track. Because if I just try a bunch of numbers, I could just try them at random, right? I could try a bunch of random numbers, and I could keep going until I got tired of it, right? I'm not sure I would have an answer at that point. So how do I structure the ones I try? Yeah. Yep. Okay, so that's a great approach. So I could essentially start at, I wouldn't start at 0 because, I know 1 is a candidate, and dividing numbers by 0 produces, an indeterminate result. So I might start at like 2, right? And I start at 2, and I say, does 2 divide both numbers equally? If so, I store it. Otherwise, I go on and I try 3 and I try 4, and I go that way all the way until I get to the smaller of the two numbers. Why can I stop once I get to the smaller of the two numbers? Why is that safe to do? Yeah. Yeah, the greatest common denominator can't be larger than the smaller of the two numbers, because once I get, if it's 17 and 38, right? Once I get to 18 and 19, those are numbers that will never divide 17 even. So I can stop as soon as I get to the minimum value. Okay, so that's not a bad approach. I can think of a way to make it a little bit easier, so trying a lot of numbers, not a bad idea. It would be great if as soon as I found one I could stop. So how do I arrange my algorithm slightly differently so I can do that? Yeah. Yeah, what if I start at the value of the smallest of the two numbers and I count down? So I start at, the smallest of m and n, and I count downwards. Now, as soon as I find a number that divides both evenly, I'm done. Because I've set up the problem, so I know that that's the maximum number possible. It's possible that the first number I try is the GCD. If I have, a larger number that's a multiple of the smaller number, then the smaller number is the greatest common denominator. It divides itself, and it divides the larger number. Otherwise, I keep going, and eventually I'm going to get to a number that I know works. So this is an approach that falls into a category of algorithms that I just want us to be aware of, right? These are sometimes known as brute force solutions. I used to, I used to review papers for conferences, and there was some author who wrote papers that I would sometimes get assigned to who would always refer to this as a brutal force solution, okay? So it's not brutal force. We are not trying to kill the problem, right? Your goal is to solve the problem, all right? So brute force, the brute part of this is that we're not being sophisticated. You know, we're just trying a bunch of numbers. Like someone said, let's just try a bunch of numbers. Okay, great, right? So let's do that. So we're essentially, and the brute force definition is a little bit more clear about what that means. We're gonna systematically check all possible solutions until we find one. In this case, all possible solutions is essentially the smallest of the two numbers all the way down to like 2, because we know that 1 is always the GCD, right? So 2 is the last one I really have to check, right? So essentially a brute force, and the brute force approach is a very general technique. There's a lot of problems that we can solve this way. Essentially, as long as I can figure out if a particular answer is correct, I can apply a brute force solution, because I just enumerate all of the possible alternatives until I find one that works, right? Now, here's the things to keep in mind when you implement brute force solutions. One is that computers today, this is one of the things that, you know, I don't think that any of us really have the mind to comprehend. You know, when you think about, for example, the age of the universe, it's hard to imagine, you know, billions and billions of years. That's a time scale that our human brains just don't deal with very well, right? It's hard to think about. It's equally hard to think about how much faster computers are now than they were 10, 20, 30, 40 years ago. The rate at which computer power has increased is just astounding. There's never been anything like it in human history. I mean, that's, you know, one of the reasons I'm so excited that so many of you are here learning about this stuff, right? Is we've been, you know, the computer engineers, you know, tease them if you want, right? But they've given us this incredible gift, right? All this computing power, and the amount of it we have and how fast it's accrued, again, is something that just like our little human brains can't quite appreciate, right? But you've got it, right? The phone in your pocket is more powerful than supercomputers were in the 60s and 70s. That's actually true, right? So computers today are very fast. What does that mean? It means that these type of brute force approaches sometimes are fine. You know, sometimes they're totally okay. They're gonna be able to solve the problem in an acceptable amount of time when you're performing certain calculations. It's okay to use a simple algorithm, right? And so a lot of times when we talk about algorithms, we're gonna talk about, okay, well, what's the simplest possible approach? If I'm searching for something, I can just go through the entire array one element at a time and look for the thing I'm looking for, right? That's a brute force approach. I'm just enumerating all of the possible options until I find the one that works, okay? And in certain cases, particularly when you're working on small problems, even medium-sized problems today, because of how fast computers have gotten, this is totally okay, right? Once things get too slow, then you could reach for something sophisticated. But it is certainly, you know, I come from a computer systems background, and computer systems people in general are also fairly suspicious of fancy stuff, mainly because we think you're never gonna implement it properly, and it's gonna have bugs, and it's gonna crash my system over and over again, and the amount of time it takes you to do your sophisticated thing is probably gonna be more time than it takes me to do my simple thing, and the answer that I will get is just as good as yours, right? So again, I mean, let's try this, right? So we have now a simple approach for GCD. Let's implement it here. So we're gonna create a method called GCD that takes 2 integers. We'll say we're gonna use the math package to get the minimum of the 2. Say I is greater than or equal to, greater than 1, I plus plus. That's the number that I'm trying. So I'm starting at the smaller number, and I'm working down. How do I test whether or not the number divides both of the numbers that are my inputs? I can say if first remainder I is equal to 0 and second remainder I is equal to 0. Then I return I. What do I do if I get all the way to the bottom of this loop and I haven't found an answer? At that point, I know that the GCD is 1. Yeah. Yeah, 1 is always a common divisor of any two integers. Okay, so, uh-oh, what's going on with my slide runner today? Let's try this again. So the problem with our backend systems are here, okay. Oh, I have to take ints. Okay, let's do for int I is equal to, oh, I had a bug on that. Somebody probably saw it. I minus minus. Yes, I plus plus is not gonna produce good behavior. All right, so again, if the remainder when I divide the first one is equal to 0 and the remainder when I divide the second one is equal to 0, then I'm done. Otherwise, I'm gonna return 1. Okay. That works. Okay, good. I mean, did anyone feel like that was too slow? I don't know. Let's try it again. Let's try a larger number here. Random numbers. Oh, it's too long for an int. Okay. I mean, that seems fine, right? Like, this is not slow, right? And if you were, depending on the kind of problem you were solving, this might be okay. Now, I mean, we can certainly, get this to start to perform more poorly. Let's change these into longs. And now let's use a larger number here. Oh, and I have to put my long literal next to it. That's, that's still pretty fast. I mean, let's try a longer number here. Oh, you know what? It's because it's gated by the longest one, the minimum, okay? All right, so now I can get it to timeout, okay. So if I give it a long enough value, now it's taking a little bit too long to run. Okay, you guys might have been able to see some of the properties of the solution, but for small integers, this is not a bad approach, right? And this is, again, this is the brute force, not brutal, brute force solution, right? I'm just gonna try everything. Now again, on some level, I feel before we start talking about runtime and big O analysis, I just want to remind you that again, you guys have access to this really beautiful gift that the ECE people have bestowed upon the world. We have an incredible amount of computing power out there, meaning that you don't always have to do the most sophisticated thing in order to change the world. You can write really impactful, important applications and solve important real-world problems today without forcing yourself to solve complex algorithmic challenges, okay? Real programming is not solving a series of elite code or interview questions, right? Those are fun, but there's a lot of places where we need better technology and need better computing and need more people working in this space to solve problems where you don't have to do that. Or, again, maybe after your company has 1 million users and things start to slow down a little bit, then you can be like, okay, well, let's make things a little bit more sophisticated, right? You don't necessarily have to do that right out of the gate. But at some point, some of this may start to catch up to you, right? Speed will start to matter, or the performance of these simple brute force algorithms will start to become a problem, right? You might start to be embarrassed that you have to throw a lot of computing at a problem that seems like it's a little bit, that it could be solved in a more efficient way. So at some point, again, like once your startup hits it big, you're gonna be paying a bill every month to Amazon or Google Cloud or whatever, and you're gonna start to wonder if you can make that bill smaller. And on some level, that bill is you're paying for compute. You're paying for the amount of cycles, the amount of computation, the amount of calculations those computers have to do on your behalf. So if you can do things more efficiently, while solving the same problems and satisfying the same set of users, then that's gonna allow you to run the entire thing more efficiently and create more opportunities, right? Yeah, again, you have to start paying for machines or paying for computing power. This is very common today. Computing is a commodity. It's something that you rent, but now you pay a monthly bill for, and that monthly bill is very complex, but on some level it reflects the amount of computing cycles that a cloud provider had to run on your behalf. At some point, your program might start to slow down, and customers, and this might start to make customers unhappy, and that might reduce the impact of the thing that you're trying to build, or reduce your ability to solve the problem that you're trying to solve. Or, of course, that classic, incredibly important scenario where you're in a job interview, right? And somebody wants you to show them that you can think a little bit more, in a little bit more sophisticated way about how to solve problems, right? Brute force solutions, incredibly useful in a lot of real world contexts. A job interview is not a great place to deploy one of them. I definitely don't deploy a brutal force solution in a job interview, right? Killing the interviewer is not a way to get a job. All right, so let's think about, so when we talk about algorithms, we're gonna talk about how long they take to run. And in a few minutes, we're gonna introduce some terminology that's gonna guide our understanding and gonna allow us to categorize and classify algorithms by how fast they run given certain inputs. But let's do an example of this to get us started. So, how long does our brute force GCD algorithm take to run? So let's say I'm computing the GCD of 4 and 6. How many times is that loop going to execute? Roughly. Yeah, 2, right? Because, I mean, I go 4, 3. Well, actually, it's gonna do 3, right? I'm gonna check 4, 3, and I'm gonna get to 2, right? And I'm gonna be done, right? So there's 3 numbers that I'm gonna have to check, okay? What about if I'm computing the GCD of 185 and 2045? Now, I don't expect that we have any math savants in the audience, so I'm not sure anybody knows what the GCD of this is, and that's sort of the point. But what's the best case scenario here? What's the case in which our algorithm is gonna terminate the most quickly? If what number is the GCD? Yeah, so if 185 is the GCD, and I can't actually remember what the GCD of these two examples is, it doesn't matter. If 185 is the GCD, then the loop runs once. If 5 is the GCD, clearly they're both divisible by 5, even I know that, right? Because they both end in 5. If 5 is the GCD, then this algorithm, the loop's gonna run around 180 times, okay? Okay, let's make the problem more general. What if the inputs are m and n? Okay, so now we have to think a little bit more symbolically about how to solve the problem. So first of all, this clearly depends on the minimum of m and n, right? Because the loop starts with the smallest one. So I can actually compute the GCD of a very large number and a very small number efficiently, because the small number is the one that drives how many times the loop has to run with my brute force algorithm. Okay, so let's say, given the minimum of m and n, again, what's the best case scenario here? You don't know anything else about these numbers. Just know that there's 2 of them and that there is a smallest one, okay? So best case scenario, how many times does the loop run? Yeah. Okay. The loop might run once. Why? In what case would that be the case? Yeah. Yeah. You don't know anything about m and n. Maybe n is m times 10. In that case, then I'm gonna start at n, which is smaller, and I'm gonna break out immediately. I'll immediately find the GCD. What's the worst case scenario? So this is something else that we do when we talk about runtime. A lot of times when we talk about the runtime of an algorithm, it's dependent on the inputs. A lot of times we don't know things about the inputs, but we like to think about what's the worst thing that could happen in the case in which the algorithm would take the longest to run, and what's the best thing that could happen. In what case would the algorithm take the shortest amount of time to run? And then in many cases, we'll talk about average case performance. Average case performance can be very difficult to quantify, actually, right? So, okay, best case performance, the loop runs once. Worst case performance, the loop runs how many times? Yeah. Yeah, roughly the minimum of m and n. Minus 2, but we won't worry about that constant factor. That constant factor is not gonna be important once m and n get big. So best case runs once. Worst case, it runs the minimum of m and n times, and that's in the case when m and n are relatively prime. So if m and n share no common factors, then I'm gonna have to try every number starting at the smaller of the two, going all the way down to 1, basically. Okay? Average case performance here, I'm not even going to touch because it really depends on how factors are distributed between these two numbers. But in general, you would assume that a very small percentage, if I choose random numbers here, some percentage of the time, I'm gonna get lucky, and one of them is gonna be a multiple of the other, and the algorithm will terminate immediately. Some percentage of the time, I'm gonna get unlucky, and the two of them are going to not share any common factors, and I'm gonna have to go all the way down to 1. Most of the time, they're gonna have a factor in common. And so, at some point down the way, I'm going to terminate the loop. Now we know, for example, that if I choose two random numbers, about a quarter of the time, I'm gonna get two that are both even, for example. And so 2 is at least one of their common denominators. That doesn't help me very much because 2 is very small, right? So 2, in order to get to 2, I have to go through everything else, right? I actually don't know what the answer would be if you ran this and looked at the average case performance. But clearly, the worst it can be is I have to run the loop the minimum of the two numbers, number of times. The best case it can be is I break out immediately if one of the numbers divides the other. Questions about this before we go on? What we've done is just an example of algorithm analysis. So we've taken an approach to solving a problem, and we've talked about how long it takes under certain conditions, and we've tried to generalize our discussion. So usually when we talk about algorithms, we don't care about how long they take given specific inputs. We care how long they take given general inputs. So not how long GCD takes with 185 and 2045, because I can compute that exactly. A symbolic expression that computes how long it takes if I give it two arbitrary numbers. So again, this is what we're gonna start talking about, and as we introduce new algorithms in this class, we're gonna spend a lot of time analyzing how they perform. What we just talked about there, what we did was an analysis of what's called time complexity, how long it takes for an algorithm to run. But there are other computer resources that algorithms consume as they run. Memory is one of them. So when we talk about sorting, we'll also talk about how much space in the computer's memory does a sorting algorithm need in order to run. Because we'll have sorting algorithms that don't need much space at all, and then we'll have other sorting algorithms that need a lot of extra space. And depending on your problem and how much memory you have available, that can be an issue. So we can talk about how long an algorithm takes to run. We can analyze how much memory it consumes. There's a couple of other properties that you can talk about once you talk about more complex algorithms that we'll typically not concern ourselves with. But there's a lot of different ways that an algorithm uses computer resources, and when we analyze it, we may be concerned with one of those ways or several, right? And depending on, what context the algorithm is running in, we may be concerned with some and not with others. Okay. Now again, usually, when we analyze algorithms, we want to talk about its performance for a general case, not for a specific input. And also, a lot of times what we'll try to do is talk about how the algorithm's performance scales with the size of the inputs once the inputs get very, very big. So how long does it take to sort a list of items or an array of items as that array gets bigger and bigger and bigger. One of the reasons for this is it allows us to ignore certain features of the algorithm that sort of vanish once you start to work on really large inputs. So let's go back and look at our brute force GCD algorithm. So for example, there's some amount of time required to start running the function and to kind of set up the for loop and stuff like that. That only gets done once. And then I'm inside the for loop now, and I'm essentially repeating this set of actions, this chunk of code over and over and over again. On a small input, I have to think about, well, how long does it take to initialize a for loop? How long does it take math.min to run? I don't know. But once I start looking at really, really big inputs, typically what happens is that this loop dominates the amount of time that the algorithm takes. So, you know, if you run it for a small value, it might spend 50% of its time in the loop. Once the value gets bigger, it might start spending 90, 95, 99, 99.9, 99.999. You know, eventually pretty much the entire runtime or the entire amount of time that this little algorithm takes to run on a large value is gonna be spent inside that loop. And so when we talk about algorithm performance at the limits, that allows us to ignore these sort of common constant factors, right? Like we did with GCD, we'll frequently talk about best, worst case, and average case running times. As an engineer, as well as a computer scientist, you care about this stuff, right? When you deploy an algorithm, you may want to know, well, if it gets the worst possible case, how long is it gonna take, right? Because it might get that input from time to time, right? We have algorithms out there in the world that, you know, typically perform very well, but sometimes if you give them sometimes what's called a pathological case, it can take a lot longer. We'll look at this when we talk about sorting. There are some sorting algorithms where normally they do quite well, but there's certain special cases out there where they can take a really long amount of time. We want to know about those. Frequently we want to identify those because sometimes we want to avoid actually running the algorithm on those cases because of how badly it performs. And then again, our goal here is to establish a relationship between an algorithm's inputs and its running time. So sometimes we do this by picking some small inputs and then picking larger inputs and talking about how long it's gonna take and then kind of, you know, plotting a mental graph showing the relationship between, you know, some feature of the input and then how long the algorithm's gonna take to run. Okay. I said before, the part of our goal here is to classify these algorithms, to put them into categories. And the names for these categories that we're gonna use are drawn from what's called big O notation. So big O notation is a mathematical concept that allows us to talk about the behavior of a particular algorithm as the feature that we're concerned with gets larger and larger. So for example, as the size of the array that I'm sorting goes to infinity, how long does an algorithm take to run? As the values that I'm using to compute the GCD get larger and larger, how long does the algorithm take to run? So this gives us an estimate of what happens as the problem gets really, really hard. And it allows us to estimate the relationship between some feature of the input and how long the algorithm takes to run. One of the things that we have to do to apply big O analysis, and you guys are gonna get a lot of chance to practice this, so don't worry if you're seeing this for the first time or if it's a little bit unfamiliar, we'll be talking about this every week throughout the rest of the semester. But one of the important things to do when you apply big O analysis, you have to identify the feature of the problem that you are concerned with. So with GCD, the feature of the inputs is the size of the smallest input for our brute force GCD algorithm. For other algorithms, the feature that drives performance is different. Okay, so one of the things that big O notation allows us to do is again to generalize about the performance of different algorithms and to put them into categories, to put them into classes. And I want to show, this graph serves a couple of different purposes. First of all, it serves to show you some of the different complexity classes that we're going to be discussing. It also is here to warn you about the dangers of performance and understanding your algorithm. So, let me point out something. So essentially what this graph is showing is on the x-axis, this is the size of the problem. It says elements, but whatever. I mean, this is the size of the problem. Depending on the problem, that means different things. With GCD, this is the size of the minimum, the size of the minimum of the two inputs. With an array sorting algorithm, this would be the number of elements in the array. On the y-axis is the number of operations. Again, this is an estimate of the amount of computer power required to solve the problem. You know, the number of instructions that Java has to execute internally, the amount of time it's gonna take when you run it. These are all sort of ways of quantifying computational complexity, how long it takes to solve the problem. So let me show you something that's important to understand about this graph. Down here, right near the origin, everything looks very similar. So when you run algorithms on small problems, they run fast. And this is increasingly true partly because of how fast computers are. So even if you run a terrible algorithm on a small input, it will run very fast. Now, as we increase the size of the problem, down here, hugging the x-axis, we have two complexity classes. In fact, you can't even distinguish them from each other because they're covering each other on the graph. So O1, this is sometimes known as constant time. What does that mean? It means that no matter how big the problem gets, it takes a constant amount of time to solve the problem. That is like a dream come true. That is usually not the case, right? So for example, if you're trying to sort an array, you have to at least look at every element in the array. You can't do that in a constant amount of time. But there's also another complexity class down here that's called log n. We'll talk about all of these as we go forward, right? So you can see that even as the problem gets bigger and bigger and bigger, these two types of solutions are maintaining extremely good performance. O log n is actually getting larger, but it's getting larger so slowly that you can barely even see it, right? Okay, so what's going on over here on the other extreme, right? The fastest growing complexity class that's on this graph is O(n) factorial. So this means that as the problem gets larger, the amount of time it takes to solve it grows as the factorial of the size of the problem. And you can see this is essentially taking off like a rocket ship, right, that's blasting into outer space. Right next to it is O2 to the n. So this is exponential time. This means that as the problem gets larger, n is the exponent, you know, of some number, right? 2 to the n. 2 to the n grows extremely rapidly as n starts to grow. But again, if you run these on small problems, they all look very similar. It's not until you actually start to feed them reasonably sized problems that they start to differentiate each other. The reason I'm telling you this is it's very easy today, given how fast your phones are and how fast all the computers that you use are, to think that you have a good solution because you tested it on a couple of simple inputs and it works. Then you deploy that solution. So then you go to your boss and you say, hey, I've solved the problem, you know, I've got something ready to go, we can push this out to our customers tomorrow, right? And then someone tries to run it on 10 inputs, or an input of size 10, whatever this means, right? So there is a big difference in, you know, the amount of hate mail you're going to receive, in the size of your bonus, in, you know, your chance of getting promoted, between whether you deployed one of these algorithms or one of these algorithms, right? Because as the problem gets bigger, people are going to notice, right? It is impossible to not notice the difference between one of these really fast-growing algorithms where the performance starts to get bad really quickly, and the ones down here. In the middle, we have a couple of other ones that we're gonna see pretty commonly. So down here, this is O(n). This means as the problem gets bigger, the amount of time that it takes to solve the problem grows at the same rate. And there's a lot of nice problems that are ON, which is nice. Above ON, kind of hanging out in the middle territory, there is ON log n. That means that the amount of time it takes to solve the problem grows as the number of elements times log of the number of elements. So this is growing a little bit, this is linear, this is growing faster than linear, but it's still pretty gentle. ON squared. As the size of the problem grows, the amount of time it takes to solve it grows as ON squared. When we talk about sorting algorithms, we're gonna talk about sorting algorithms that are ON squared. We're gonna talk about sorting algorithms that are ON log n. So again, as the problems get bigger, there's huge differences between the performance of these. You can imagine out here how far that ON squared algorithm has gone and how much of a difference in performance this is. This is the difference between, somebody, never using your app again and someone who is completely satisfied, right? The fact, something taking a fraction of a second, something taking multiple seconds, right? That's a huge difference. Okay, so let me go through a couple of these and we'll come back and review this next time. So let's talk a little bit more in more detail about some of these complexity classes and how you can identify them. So now we're gonna talk about the name of the complexity class and then some features of actual Java code that can indicate to you that this is what you're dealing with. So constant time, O1. O1 is usually called constant time, and this is great. This means that if I give you a problem of size 10, it takes a certain amount of time. If I give you a problem of size 10 million, it takes the same amount of time. This is almost never the case. But there are certain operations in Java that are constant time that we want to identify. So for example, assigning variables in Java is constant time. Pulling a value out of an array in Java is constant time. So this operation right here, where I take an array and I look up, in this case, the 11th value in the array, that's constant time. So this is, and when most of the algorithms we talk about, this following a reference, constant time. So this is, again, not a particularly useful algorithm, but it's a building block for other algorithms that we're going to see. Assigning one reference to another reference variable, constant time. Setting up a for loop, constant time, right? A lot of these things, take a certain amount of time, but they don't, the amount of time it takes to look up a value in an array does not depend on which index we're looking up. It's, so looking up the first value, the 10th value, the 100th value in this array takes the same amount of time. Okay. ON. So, ON means that the number of steps it takes to solve the problem scales as the size of the problem itself. And this is still a pretty good result in most cases. Because again, let's think about some of the algorithms you guys have already implemented. So finding the maximum value in an array. In order to do that, I have to check every value. There's no way to get away from checking every value in the array if I'm looking for the maximum, if I don't know what those values are. So if you give me an array of 82 values and you tell me, find the maximum, I have to check every one. I can't only check half or the first 10, whatever. If I don't look at every one, then I'm not guaranteed to find the maximum value. So there's a bunch of problems, including a lot of the simple algorithms you guys have been implementing already, that fall into this category, particularly when we're doing things like finding the maximum over an array, searching for an element in an array, finding the minimum value in an array, stuff like that. All right, so if I give you an array and there's no guarantees about the inputs, they're not sorted, they're not arranged in any way, then anytime I have to look at every element in the array, that's ON. One of the characteristic features of ON is a single loop. So here's an ON algorithm. This is computing the sum of the elements in an array. This is constant time up here, and then I have a loop that goes through every element in the array. So computing the sum of an array with 10 elements means that this loop is gonna have to run 10 times. Computing the sum of an array with 1,000 elements means that this array loop's gonna have to execute 1,000. Okay, we'll pick up here next time. The MP3 early deadline is today. You know, get to the point threshold. Good luck with that. I'll be down helping in office hours today, but I'm not gonna hold my usual 1 to 3 ones. I will see you guys on Wednesday. Good luck on today's quiz if you haven't taken it already.